We're looking at this oscillating LC circuit. We're given the inductance and the capacitance. We know that the current maximum is when time equals 0, and we're trying to figure out how long it would take to charge that. There's technically two ways to solve this, but we'll do it the harder way first. We're going to compare the Q of t equations and the I of t equations. And we're going to know that this is I max, and then some sine. And then this is going to be the Q max times a cosine. But we know that at t equals 0, essentially this is all going to go away, the sine function. But so we want that to equal 1, right? We want the sine function to equal 1. In order for the sine function to equal 1, what's inside has to equal 90 degrees, or pi over 2, because technically we're looking at angular frequencies, and that's radians per second. So we're going to use the radians. But if the time thing is already gone, so remember this is t equals 0, so there's really only a phase constant left. So that must be pi over 2, that phase constant. So we're kind of starting in a weird location, but we're shifted over a little bit. That's fine, because when we come back to this equation, we know that has to be pi over 2 as well. But we want to essentially figure out how long it would take for this thing to reach the Q max. In order for this thing to be at maximum, the cosine has to equal 1. And in order for cosine to equal 1, then the angle that's inside has to be equal to 0 or 180. And if that's the case, then we could set up the equation WT plus this thing, which we know is actually pi over 2, is supposed to be equal to 0 or 180. I'm going to choose 180 because it's going to be a little bit easier to get there if, remember that this is supposed to be 90, and then WT would be equal to 90. So we're going to have to make that equal to 90. So WT is equal to 90, but it's pi over 2. Okay? So this is kind of the long roundabout way to do this, but remember that the W is supposed to be 1 over the square root of LC. And if we plug that in there now, we're getting closer to a familiar expression that maybe you would recognize once we're in this form. Pi over 2, and then times the square root of LC on this side. This is actually one of the equations for period, because we know that period is supposed to equal 2 pi times LC. It's very similar. So essentially, one of the shortcuts would be to kind of say, oh, well, I already know the period equation. Let me just sort of think about this a second. And, you know, obviously, these two are 90 degrees apart, so that's a quarter turn. So if you want to go from 0 to full, you just need a quarter turn. So you could technically take the entire period, which would take, this is the entire period, and just divide that by 4. So if you divide that by 4, then you'll get the same expression over here. You would get pi over 2 square root of LC, because that is just a quarter turn. Okay, so we could divide the period by 4, or we could take this roundabout way. But now we have our answer. Should be able to plug that into the calculator by saying pi over 2 times the square root of 62 millihenries times 3.8 microfarads. And we should get 7.62 e to the negative 4 seconds. And that's how long it would take to charge this.